So, friends, good morning and welcome to this lecture series of geomorphology. Today, we will continue with this coastal geomorphology, and in the last class, if you remember, once we are talking about this formation of this coastal plains, its modifications, its coral reefs and something else. So, today we will talk about this sand distribution along this coast and how sand migrate, how different depositional structures they form due to this sand movement, and whether this continuity of these sand movements will break somewhere, and if it is breaking, what were those components or what are these factors they are responsible for breaking this continuity of these sand sheets. So, here if you see, if we are taking a cross profile of a seaward to land, then we will find there are two major zones of sand generations or the sand movement. So, one is very close to the shore, another is close to this breaker zone, and here it is close to shore, another is close to the breaker zone. So, now once there is a breaking waves, there is a wave which is breaking somewhere. So, that means it produces or it affects, it allows tremendous stress on this bottom. So, that is why it the sand which is available, the free sand which is available comes to in suspension mode. So, once this sand comes to a suspension mode, it is easily transported towards the coast. Similarly, the another zone where this is intense sand erosion is the swash zone. Swash zone and another is called backwash zone. Swash zone is called, other way called it is a forewash zone, or a forewash zone means a sand is moving towards coast, and backwash zone it is coming away from this coast. So, here one zone is the most important is this under breaker, and another zone is the swash zone. So, these two zones here and here they produce more sand, and there will be sand movement towards the coast, where the small waves run off the beach and collide with the backwash. Backwash means those, if you see here, one is swash, another is backwash. Swash is forewash, that means once wave is moving towards this coast, that is forewash or swash, and it is coming down, that is called backwash. So, in these two zones they are responsible for this sand movement to the coast, and those sands which was deposited along this coast, they also migrate both along the coast and across the coast. This migration along this coast is due to littoral currents, and this migration across this coast you due to this swash and backwash. So, here in this figure, if you see, major dynamic zone in the near shore zone is a sandy coast, two regions of maximum sand suspension and transports are shaded here. These two zones are here, and the sand transportation and sand suspension zones are there. And if you see here, the net movement is movement of sand is along this coast, it is parallel to the coast. However, here the sand is moving to an angle and it is coming vertically. So, that means this type of movement, if you remember when we are talking about creep movement in mass wasting, same type of movement, but in a vertical scale, it is in horizontal scale. So, here in the vertical scale, that was the creep movement, the same type of movement was there, and here in the horizontal scale it is the movement along this coast is there. So, anyway, suppose a sand particle was here with this swash zone, it is moving here at an angle and coming vertically. Similarly, it is moving angle and coming vertically. So, the net movement is along this coast, and this movement due to this littoral current. Now, the question arises, how this littoral current generates and what is their role in migration of sand sheet and formation of this sandy coast. So, here between these two eroding zones, when the waves are approaching at an angle, if you see here these waves are approaching at an angle, one vector of this water motion is parallel to this shoreline and a powerful littoral current is generated. Here this region or the mechanism of littoral current generation is been described. That means, the wave has to approach this coast at an angle. If the wave is parallel or wave is vertical or wave is at an angle. So, that angle which is wave is encroaching this coast, that wave is capable of generating a strong littoral current. So, when waves break nearly parallel to the shore, only weak littoral current are produced and sand movement in the surf zone is nearly perpendicular to the beach. So, here if it is perpendicular to the beach, that means there will be no littoral current actions. So, if this wave is backing parallel to the coast, that means parallel coast means there is no effective sand movement or effective along the shore sand movement is there. But if it is breaking at an angle to this zone, angle to this shore, that means a strong littoral current is generated and that current is able to transport huge sand along this coastline and forming the sand sheets. So, in a marine environment, if you analyze the geological records or these stratigraphic sections, you will find a lateral continuity of sand to huge distance in terms of kilometers of hundreds of kilometers. Those continuity of the sand sheet so uniform nature is due to this littoral current, and this continuity is break by this rivers, by other factors like this ridges, these notches like that. So, until unless these barriers are there, the sand sheet can migrate along this coast to hundreds of kilometer distance. So, that means I can conclude here that these waves which are breaking at an angle to this coast, they are producing strong littoral current which is capable of migrating sand to large distance. So, with a breaker angle and height that generate a littoral current of 30 centimeter per second, sand moves along the shore, but with outward component towards the breaker line. Here if it is a slow movement, suppose a breaker angle and height which is generating a littoral current, but it is 30 centimeter per second, that means it is a slow littoral current. So, that means slow littoral current will not allow the sand to move along this coast or parallel to the coast. Instead, it will allow this sand to move across this coast. That means, here the swash and backwash, the backwash movement will be dominating rather than the littoral current. So, in that case the sand along the shore will not move, it will move outward component towards the breaker line, that means toward the sea it will move. But if a littoral current velocity is 80 to 100 centimeter per second, so a strong movement of sand parallel to the shore occurs like a shallow fluvial rivers. So, one if you suppose if you compare, suppose the sand is moving along a river, it is confined between two banks of a river. Similarly, if we are moving the sand along this coast, so we are comparing this coast parallel movement of the sand along, suppose within a confined river system, that means this two coast, one is parallel to this shore and another is, so that means here one side is your shoreline, another side is the wave. So, through this sand is moving, that means if you are taking a cross section, it will look like a river. So, that means here we are concluding that a strong littoral current to generate which will allow this sand to migrate or to move along this shoreline parallel to the shoreline, this littoral current velocity should be 80 to 100 centimeter per second at least. So, that a strong littoral current and a parallel component will be there. The parallel component, the coast parallel component will be strong enough to migrate the sand from this coast, from one part of the coast to another or along this coast. Otherwise, if it is a slow movement, it will be a slow littoral current, that is 30 centimeter per second. So, rather than parallel migration, the sand will migrate towards the sea or towards the breaker zone. Within the surf zone, a ribbon of sand 100 meter or more with width and 5 to 10 centimeter in thickness moves at a rate 1000 meter cube per day or more. So, that means the sand sheet migration, how much sand is migrating at a particular cross section. That is, if this current it is 80 to 100 centimeter per second littoral current is there. So, it will create a sand sheet of 100 meter or more width and 5 to 10 centimeter in thickness and moves at a rate of 1000 meter cube per day. So, this amount of sand can migrate with the 80 to 100 centimeter per second littoral current. Under such dynamic conditions, sandy beaches can adjust to changing wave and tidal energy within hours, and near shore profile is constantly regarding to change of conditions. So, that means I want to say here this is a dynamic condition. So, depending upon this current velocity or this tidal current velocity, depending upon the littoral current velocity, depending upon this wave. So, this condition is dynamic. Sometimes the sand may migrate, some may not migrate. So, the constantly profile, if minute by minute profile or hour by hour profile will take across the shore, we will find the changes. So, these changes is nothing due to the dynamic behavior of this littoral current, these waves, the sand supply, the breaking waves like that. So, mostly the sandy shores can be divided into distinct littoral cells ranging the length from about 1 to 100 kilometer. Each is defined by sandy score, transportational segment and sand sink, where sediment is removed from the system. Remember, when we are talking about this modeling in the geomorphology or introductory class, we are discussing that this sand sheet, it may not be continuous forever. So, there are some segments or there are some factors, that is, suppose for example, in this figure you see they are the streams or the rivers they are coming, and this is this littoral current, this is the sand sheet which is forming along this coast. Now, you see this is one separate sand sheet, this is another separate sand sheet, this is another separate sand sheet like this. So, that means within this sand sheet they are distinct domains. So, distinct domains, that means it has their own sand production house, the sand transports within that and sand sinks there. So, where will they suffer? For example, we are considering here, these are the zones where sand is generated, because their wave they are hitting here and this coast and forming generating this sand. So, the sand is migrated due to swash and backwash, and they are migrating laterally by this littoral current, and once they are reaching along this river mouth here. So, this sand is removed from the system, either they will migrate from the depending upon the dominance of tide and waves. So, either the sand will be distributed in this way or the sand will be distributed in this way. That means, from this system we are removing the sand. So, that means I want to say this entire length of this sand sheet can be divided into segments, and each segment have its own source or sand source. They have some transportation segment, they are transported either by wash and backwash, and then there is a sand sink where the sand is removed from the system. So, what would be the source for that? Source include new sand added to this littoral system from offshore, from river mouth and from eroding slick cliffs. So, these are the different source, either from the offshore that will be added offshore due to the offshore current, due to these breakers, then from the river mouth, it is from these fluvial systems, they are contributing sand which is coming from this continental system, and then from the eroding slick cliff near to the coast, from the eroding slick cliffs the sand is added to the systems. So, there are three sources are there. Similarly, sinks are those places where sand will be removed from the system. So, that means sinks are places where sand is lost from the system by wind transport inland. So, that means wind transportation is another factor. During wind transportation, sand will be removed upstream, it will move from the system, and Then by tidal current deposition in sheltered lagoons are there due to tidal current. Once there will be tide, the tidal current will remove sand from here and it will deposit it in the lagoons. Then by reef currents into deep water, reef current, when is current moving down, the sand will be removed from the system into the deep water. And rarely by being trapped in the heads of submarine canyons. Submarine canyons are there. So, there are chances the sand is removed from the system that will be trapped within that submarine canyons, okay. And that led to the deep sea basins. So, that means these are these 4 distinct mechanisms or those 4 mechanisms through which sand can be removed from the system. Sand can be added, sand can be removed. Within that, sand transportation occurs, and transportation is due to this backwash and wash zones and due to this littoral current movement. Then we will discuss here about the wave refraction. So, we have already discussed about the reflections of these waves. When there is cliffs are there, wave they hit these cliffs and reflect back. Similarly, there are wave refraction cause mobile beaches to change their orientation readily until the plan view of the shoreline conforms closely to the shape of the refracted wave front. So, that means you see here we have waves and these are these headlands, and if you take this profile of the headland, that will be like this. So, that means gradually they are plunging into the sea. So, in that cases wave refraction occurs, and as we know earlier, due to this wave refraction, maximum energy is concentrated here, and here these zones are the wave dissipating zones, and here they are waves concentrating zones. So, that is why these parts will be removed or eroded, and the removed material that will be deposited here. So, new beach will generate here, and here the sands will be removed, material will be removed. So, wave refraction, it causes a mobile beach, that means one side beach will be developed, another side beach will be eroded. So, this type of movement, this type of change in these beaches, that is done and by this wave refraction, and this shape of this beach, how it will look from this aerial view, that depends upon at what angle the wave is refracting and what angle this refracted wave is approaching along this coast. So, with a geological time within hundreds of years or thousands of years, you will see this shape of this beach is taking that shape which is the dominant angle of wave refraction, and how this refracted wave, at what angle the refracted wave is approaching to the sea, this beach will take that shape. For example, if you see here, if you see, this is clearly seen that the wave here, these are the refracted wave like this, and you see this beach shape is like also like that. Similarly, here this refracted wave, they are like this, and here if you see the beach is of that shape. So, that means with a geological time, the beach will take that shape from aerial view, that shape is confined, the shape is followed by the shape of this refracted wave from this breaker zone. So, that is why in the worldwide, if you see these beaches of these worldwide beaches, this beach has taken their own shape, and the shape is dependent on the dominant angle of wave refraction. On the coast with alternating headland and beaches and a dominant swell that approaches obliquely, beaches assume to half-hearted or jetta-form curvature. For example, if you see here, this is called jetta-form curvature. For example, one is straight, another is curved. Similarly, there will be straight, then will be curved like this. So, jetta-form beach, if you see here, one component will be straight, another is curved, and this is headland, this is headland. So, within the two headland there is a beach, and this wave reflection, refracted wave, they are interacting with this coast and forming this half hearted shape. The heart shape will be like this. Similarly, if you see here, this is the half hearted shape, and this is called zeta-form coast, zeta-form curvature. And zeta-form curvature, they are mostly formed due to this wave refraction. The outline of these headlands bay beaches has been shown to approximate a logarithmic spiral, and each zeta-form beach segments seem to be offset relative to its neighbors, with the straight segment of beach rotated from this mean trend of this coast towards the dominant swell direction. So, if you see here, this is a figure from eastern Australia or New South Wales. You see the zeta-form coast is like this. This type of wave refraction is there, so that for a long time, if wave interacts, the refracted wave interact along this coast, and this type of beach are developed. And if you see here, each zeta form, one straight segment is there, another curved segment is there. Similarly, one straight segment, another curved segment, and each straight segment, here it is mentioned, each zeta form beach segment seem to be offset relative to its neighbors, with the straight segment of beach rotated from the mean trend of this coast towards the dominant swell directions. So, this is the science behind it. Then if we have a coast, we have refracted waves, and each is dominant. Suppose here this is independent, this is independent, and that is why grain size, sorting and beach profiles all changes systematically along each zeta form beach. So, that means, if you take a profile along here, a profile here, a profile here, these three profile will not match. Here the grain size will be different, here the grain size will be different, here the grain size will be different. So, we know this grain size is a function of this wave action, this function of this tide current, and this depending upon this coast characteristics. So, that means, for each zeta form, this grain size will be different, the sorting will be different, the beach profile will be different. Each is nearly a closed littoral shell, and the sand supply and movement, although some sand probably drift around these down waves headlands to nourish this next beach. So, here it is assumed to be a closed system, here it is assumed to be a closed system, but it is not too close, it is completely closed or closed sensu stricto. So, there are certain sands that can migrate from this system to this system, or it can migrate from this system to this system. So, zeta form coast of northern New South Wales, this figure is taken from Google Earth in Australia. Longest beach face of this dominant swell from the southeast and trend obliquely to the line connected to the headlands. Here from the southeast, this wave is coming up and it is refracting here, and due to that this type of zeta form. So, that means, the long axis or this part, it is facing towards the refracted waves, and finally, it is forming such type of zeta form coast. Then another component along this coast, it is called barrier. So, barrier, that means, it is like a ridge of sand which is developed few kilometers or few meters away from this mainland, and this is formed due to this wave action as well as this current actions. So, along again this barrier is not an continuous one, there are some brackets, there are some breakage within that. So, there are some breakage, for example, here this is called tidal inlet. So, during tide, during high tide, sediment will migrate in this way, during low tide the sediment will migrate this way. So, we will find eve tidal delta, then flood tidal delta. So, along this or across these bars, across this barrier towards the seaside, we will get this eve tidal delta, and towards the lagoon side, this side is the lagoon, this is tidal flat. So, towards the lagoon side we will find this flood tidal delta. So, this sand barrier, this is also not permanent, it migrates from one place to another. Along this coast it migrates, across this coast it is also migrates. So, its stability and instability, that depends upon the wave action, depends upon the tide, depending upon the sand supply. So, all those factors that combinedly work together to say whether this tidal barrier or this barrier will be sustained for what geological time or to what extent. So, massive sand ridges extend for hundreds of kilometers along many coasts as barriers, only rarely tied to headlands. So, that does not mean, so they need two headlands to tie between that. So, they are independent, they may or may not associated with the headlands, but their existence depends upon this wave and tide action and the sand supply to this coast. And this is a satellite imagery. If you see here, this is the barrier it is generating, and one barrier is again divided into two different segments. So, how this will happen, either two barrier will coincide to form one, or they will divide into two, one barrier will divide into two, that depends upon this mechanism of this sand supply, the mechanism of the wave action, the tidal action and river action, like that. So, barriers are large constructional landforms, they are depositional landforms as much as 1 kilometer wide, 100 meter height to the crest of the highest dune. Unless underlain by a relict landform, the high relief is aeolian. This is very much important to understand here. So, here you see this is a profile. Now, see, this is a barrier, and through this barrier, this part of this lagoon, this is a lagoon and this is the main sea. So, lagoon is cut off from this main sea, or lagoon is formed due to this presence of this barrier, and its height, its hundreds of meter, and its length is hundreds of kilometer, and width is about 1 kilometer or more. So, at the top part of this barrier, the free sand is there that can easily be moved by this wind or this near shore wind action. So, that is why this drier parts which is above this mean sea level, these are frequently modified by this wind action, this is aeolian action. So, that means one part which is stable, which is water saturated, so it is heavy, and another part which is the upper part which is dry, that is migrating, that is continuously migrating due to aeolian action. So, sand moving onshore or along shore is blown off beaches at low tide, and if a plentiful supply of sand is available, it is replaced and the barrier grows. If sand supply is inadequate, this barrier is eroded or driven landward by washover and loss of sand into the inlets into during major storms. So, now it is to understood here very clearly that the sand at the beach environment, sometimes it will be inundated by this or it is covered by this high tide, and sometimes it will be exposed due to the low tide. So, once it is in the low tide condition is there, so in during low tide these aeolian actions are very prominent. So, this sand will migrate from one place to another place. So, that is why if the sand supply is continuous, sand supply is sufficient, then barrier will grow. Otherwise, if the sand is not sufficiently being supplied, so the size of the barrier will gradually decrease, and finally, there will be a loss of sand from this barrier, and eventually the barrier will vanish. So, this is the mechanism how the barrier either it will grow or it will vanish, that depends upon the sand supply, depends upon the wave action, depends upon the wind action. So, I think we should stop here and the next class we will talk about more about how the barrier grows and what is the mechanism, how to what extent the barrier can migrate and what is its role to control or to contribute the coastal geomorphology. So, thank you very much, we will meet in the next class.